So let's now talk about the intuition for understanding how the backpropagation of error mechanism works and what's going on in the training of a neural network with hidden units. So imagine we've got a 3-input network with 2 layers and overall 2 outputs. So we've got an input which is going to be a vector. It's going to be a 3x1 input vector, which is basically then passing its data to the first layer. We've got the first layer has got two nodes, so it's going to have 2 outputs, if you like, from the first particular layer, which is going to go on to the last layer. And because it's got 2 outputs and it's got 3 inputs, we end up with a weight matrix, which is going to be a 2x3. Like I said, we've got 2 outputs from the lower layer feeding into the upper layer. So this is going to be a 2x1 matrix in this particular case. And then since we've got 2 inputs to the upper layer and 2 outputs from the upper layer, we have a simple 2x2 weight matrix for the upper layer here in this particular example, and a 2x1 output vector corresponding to the outputs of the nodes. Let's think about then, first of all, doing the forward propagation. So this is something we always have to do, even if we're training the network, but sometimes it's all you need to do if you're using it in recognition mode. So we'll apply the inputs to it. And if we're doing this in a training phase, then obviously that we also know what the target is. So we've got the input and the corresponding output, so we can train this system using supervised learning. What we do then is we'd calculate the internal activations as we go along. So the outputs of the intermediate nodes here, A1 and A2, would just be calculated by W1 times X, and then we take an element-wise sigmoid. And in this particular case, we'd end up with a 2x1 set of activations. And then these activations would then pass into the upper network, if you like. And we can calculate that quite easily by multiplying this weight matrix by the activations coming into W2A. And that'll give us, then we take the sigmoid and then we get the overall outputs. Obviously, we're not thinking about bias terms or anything here. This is just to keep it simple. In fact, we're not going to think much about sigmoids in a second either. So basically, if this network has not been trained and we've got initial values for the weights, then we're going to end up, when we put the input in, with a very poor prediction of what the target should be. So consequently, when we start off training these networks and we've initialized the weights randomly, say, we end up with a huge error at the output, generally speaking, because the prediction with the weight that we've got is not appropriate to generate the target. So we can define an error as just basically the difference between the target value and the output value. Now in practice we'd use a squared error, and in practice we'd have sigmoids all the way through this network as well. But now, just for the sake of intuition, thinking about why we should change weights the way we do and how we can get an effective error at the hidden layer, so we can train the lower the weights, we're going to just assume that we've got linear operations and we've got this simple linear error. Of course, in practice you wouldn't do that, but this is just for the hand-waving arguments of how this thing can work, basically. So let's think about how can the network, from an intuitive perspective, improve its weight matrix so the output error is reduced. So let's first of all concentrate on the second layer weights. That's these ones here, because they're closest to the output. And the closer we are to the actual output, then the closer we are to the actual error we can directly compute. And we see then that the second layer, right, this second layer network receives obviously inputs which are the activations from the lower level, right? So we've got this A1 and A2 feeding in to this upper network. So consequently, there's 2 things we could do to improve the output here by just thinking about this upper network, firstly, we could improve how the activations that are going into it are, basically. And the other thing we can do is we can improve the weights in order to get a better prediction on the basis of the activations that we actually have. So there's a couple of things we can do. So let's think about the output layer again. We're now going to focus on this output layer, and we've just basically zoomed in on just that part here. Let's now assume the situation as follows when we have a large activation on this node A1, right? A small one on A2, and we're going to imagine there is a large error at output 1, right? So in other words, output 1 needs to be moved closer to the target value, right? So we need to make that bigger. So how are we going to do that? Well, first of all, we notice that because A1 is big, right, it's more the input going from A1 via this weight W11 will have a bigger effect on O1 than the input A2 going via this other node W12. So basically, A1 will have a bigger effect on O1 than A2 will. So the weight that's connecting A1 and O1 is going to be more important. So the output is going to be more sensitive to changes in that weight than it would be the other weight, for example. So therefore, in order to reduce the error, what we need to do, obviously we've got to change weight W11, right? And it's more sensitive to what's coming in from A1, and it's more it's basically concerned with the value that we've actually got there as an error is also basically affects how we're going to change W11 as well. So the error at the output O1 is going to be an important factor on how we change the weight. If there's a really big error, then we need a big change in W11. But similarly, if A1 is also really, really big, then that's also going to be really important for it. So we need to change basically the weight that connects A1 and O1. So the weight W11, that's this one here, we need to change that in proportion to the error, right? And we also need to change it in proportion to the input it's getting, which is A1. And we notice also, and we should also, if we look at the other output here, we should also adjust W21. That's this one here. Sorry, W21. No, that's this one here. In proportion to how strong the input A2 is. So if A2 was, we've said it's really small, in which case it doesn't make much difference. But if A2 was big as well, we'd also have to take into account that that's also going to be important and change W21, which is this one coming up here, in proportion to that A2 value as well. So the general idea then is we change the weights proportional to, first of all, the error at the output and also the input values, right? So the change in the weights that we're going to have is going to be proportional to the error that we've got and, in fact, the transpose of the activation coming in. So weight change depends on, or is proportional to, input and the error. So changing weights proportional to input and error is actually very reminiscent of the Hebbian learning rule. So if you haven't heard of that, maybe just look it up. And what we also see is this required weight change actually is what we've already derived using the delta rule. Well, it is the delta rule. And because we're in this instance here, we're actually just looking at a linear system. This is the delta rule for a linear network. Now, we've talked about how we can change the weights in the output layer, right? But now we have to worry about how can we change the weights in the layer below, right? And the first thing we notice is, well, something else which affects O1 and O2 in this network that we've got here, apart from changing the weights. That's good. We want to change the weights as much as we can. But we also need to change the activations if we can. So if we can change A1 and A2, that will also improve the output. And in practice, of course, we need to do both. So how can we actually do that? To what extent then does A1 and A2 actually depend on the outputs that we've got? Well, actually, if you think about it, the outputs are dependent on the connections to those particular activations, right? So A1 and A2 are dependent on the connections. So looking at O1, we see A1 is connected via W11 and A2 is connected by W12, right? So these two weights, W11 and W12, basically tell us how much activations A1 and A2 depend on O1. So if this weight is bigger, then the more important it is, basically. So what we have to do is we have to scale this effect with the actual by the weight. But we also have to notice that if we're looking at, how much do we need to change A1, not only does it depend on the output 1, O1, via the weight here, it also depends on output 2 because there's another weight here, right? So there's going to be another basically dependency coming in. So we've got to take a sum, if you like, across all the output errors in order to indicate how much we'd like to change the activations. So we can basically write down how much we'd like to effectively change activation A1 as being proportional to, first of all, it's the error at O1, right? So we need to change it in proportional to the error, because if there's no error, we don't need to change anything. If there's a big error, we need to change it a lot. And we also need to change it in proportion to the strength of the weight. So in this case, change in A1 depends on error at O1, so that's T1 minus O1 times W11, which is the weight. But also, there's a term affecting how we should calculate this change coming in from the other output as well. So this is also affected by an error at O2, and in this case, also the weight W21, right? So in other words, we've got a sum here of two components. We've got the change that we want in the activation is proportional to weight W11 multiplied by the error output 1 plus weight W21 multiplied by the error at output 2. And we have to do exactly the same thing now for A2. It's just that we basically have different connections. We've got the same outputs, right? We've got the same error that we have to calculate here and the same error we have to calculate here, but now we've got different connections. So we've got this is now W12, right? This term here, and this term is W22. So that's where we get those equations from. So those are basically two equations telling us how much we'd like to change the activations. In fact, what it's telling us is effectively what is the error in activation at that point, which is really good because now we've got a way of saying now we've got the effective error at activation at the hidden layer. Before we only had the error at the outer layer. So we can now treat this optimization that we're going to do now in exactly the same way as we treated the output layer. But before we do it, let's just write this all down in matrix form and see what it looks like. Very easy to do. We've got two values. We can put them in a vector. We see that again we've also always got this output error at O1 term and output error at O2 term, so we can basically put those, stack them up into a vector, and then we see that we've got these four values that multiply by these things, and if you actually multiply that out, you'll see that it comes to this. So W11 times T1 O1 plus W21, there we go, times T2 O2, and so on for the other output. Now, interestingly, what we can do, we notice that this isn't the weight matrix at the moment, because basically this is term W11 and this is now term 21. And actually, if it was the weight matrix, it would be W11, W12, W21, W22. But we can actually transpose the weight matrix in order to get what we've got above here. So we can rewrite this expression in terms of the transposed weight matrix. So basically, in a nutshell then, we're saying now that the vector change that we want, the effective error that we want on the output of the lower network, so the hidden activations, is proportional to W2 transposed multiplied by the error at the output. Okay, that's where those terms come from. So this is actually really nice. So what we've managed to do is we've managed to get an error at the output and then calculated an effective error at the hidden layer. And because of that, we can just do what we normally do when we're calculating the change in weights that we need. And in this case, it's going to be, if this was a linear network, it would be the error at the output multiplied by X transpose that gives us the update. In this case, it's the error at the activations here that we've got that's giving us the update. Right. So in this case, we've got this delta A term rather than the error term. And we know that the delta A term, we just calculated it, is basically it's the W2 matrix transposed times the output error. So it's basically taking the error at the output and passing and multiplying it, if you like, transforming it by the transpose of the weight matrix here in order to get the activation error going in, right? And consequently, if we start substituting everything in here, we can end up what this comes out to. We're substituting delta A into the first expression. We end up with delta W1, which is how we should change the weights in the first layer, is proportional to, we've seen this before, W2 transposed multiplied by the output error multiplied by the overall input to the system. Okay, which is, again, the update rate, update rule for a linear network. And like I said, it's for a linear network because we haven't had any, we haven't taken any notice of sigmoids in this derivation, because it was basically an intuitive walking through trying to understand why things are the way they are.